what's the crack? In this video, we're going to go over longitudinal and transverse waves, what polarization is, and basically just to make sure you actually understand what a wave is. Because really commonly in GCSEs, and I teach it this way too, we always draw waves like this, right? And people just imagine that that actually is what a wave is doing. So for example, if I was to draw the wave later in time, when we draw a wave later in time, what people start to imagine is they think the wave has moved along this way, right? But it hasn't moved along this way. Because remember what we learned, what the definition of transverse waves is that the energy is what moves, right? We're not saying the particles move this way, it's the energy of the wave. So when we sketch this dotted line, that's showing you where the energy of the wave is later in time, not where the particles have moved along the right to. So to explain this, we know that transverse waves are ones where the oscillations or the vibrations, you can use either word you want, are perpendicular to the direction of energy transfer. Okay, so again, what we're saying is the wave at one point in time is that black line. Okay, so the black line is my wave to begin with. And what that means is, again, we know that the particles, so let's say I have an air particle right here. I know that air particle, all it's going to do is it oscillates or vibrates perpendicular to the direction that the energy is moving. Okay, so the energy is moving towards the right. The particle is vibrating or oscillation perpendicular direction. Right, so it's not moving left or right. Let's say we've got a particle here at one point in time, it's oscillating perpendicular to the direction of motion. I've got a particle here later in time, it's oscillating perpendicular direction of motion. A particle here later in time, again, that particle can only oscillate perpendicular direction of motion. So what we do is we basically take a snapshot of where the particles are in time. So if we take a snapshot of where the particles are in time, you can see we can get like a trace of what that wave looks like at that point in time. Okay? So again, it's a snapshot showing you where the particles are at that point in time. And we know that the particles, they vibrate or oscillate perpendicular to the direction of energy transfer. And then remember the maximum displacement they can get from that equilibrium line. So this is my equilibrium. The maximum displacement they get from the equilibrium is called the amplitude. Okay, so we can see that every single particle in this transverse wave has the same amplitude. They can all get to the same maximum height and the same, again, maximum height below the axis, okay? So again, this is our waves. The particles get the whole way up the top of the amplitude, then they can vibrate the whole way back down to its equilibrium, the whole way back down to the minimum amplitude, and then back up again to its equilibrium position. So let's say we draw the wave later in time. If I was looking at my wave later in time, I can see that if I just draw my dotted line to just extend this wave, I can see what happened to this particle is it actually moved down. Okay, I can see this particle moved down, this particle moved down, this particle moved down, this particle moved up, 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 that particle moved down, that particle moved down. So again, my dotted line shows me the particles are slightly later in time. So those particles there that show me where they are, and you can see what happened is some of them moved up, some of them up by more amounts, some of them moved up by little amounts, some of them moved down by barely any amounts. So what we're saying is, within one wave, all the particles are moving in different directions, and they're moving different amounts. So what we call them is all are out of phase. Okay, they're all out of phase in one wave. The only points that are in phase doing the exact same thing at the exact same time are the exact same point one wavelength apart. So let's say I take my solid line, and again, I draw at one wave slightly apart. And again, my dotted line is the wave slightly later in time. You can see that the waves that are exactly one wavelength apart are doing the exact same thing. Okay, the waves that are exactly one wavelength apart are doing the exact same thing. The waves that are exactly one wavelength apart are going to do the exact same thing. So all waves, all points within one wave are out of phase. The only points that are in phase are the points that are exactly one wavelength apart. So those parts are in phase. So the 2 points that are one wavelength apart are exactly in phase. All points inside this wave are out of phase. This is called a progressive wave. Sometimes you might see it called a traveling wave. So what that means is the energy transfer across the room over time, okay? So it's like my sound is traveling right now across the room. It's a traveling wave or a progressive wave because the sound is traveling across the room. However, sound is not a transverse wave. Sound is a longitudinal wave. Okay? Longitudinal waves are formed by compressions and refractions, okay? They're pressure waves. So a longitudinal wave we call a pressure wave because what happens is they're formed of compressions. So if things get compressed, all the particles are really close together at one point in time. And refraction, where all the particles are further apart at one point in time. Again, a compression, where all the particles are really close together at one point in time. And again, a refraction, where the particles are further apart at one point in time. So hopefully you can see, again, a wavelength would be those points between those two compressions. That's my sound wave. And what a longitudinal wave is, it's basically the exact same definition, but for a longitudinal wave, we say that the vibrations or the oscillations are parallel to the direction. Are parallel to the direction of energy transfer. So again, what's happening is the energy is moving towards the right and all these particles are going to oscillate or vibrate parallel to that direction of energy transfer. Okay, so what is polarization then? So again, we know that transverse waves is where the vibrations are perpendicular to the direction of energy transfer. We know some examples of my transverse waves are basically all of my EM waves. So EM waves, remember, are your electromagnetic waves. So things like radio waves, infrared, microwave, visible light, and then your longitudinal waves are things like your sound waves. Only transverse waves can be polarized. So again, what we're saying is only transverse waves can be polarized. So what does that mean? So a transverse wave is the only waves that can be polarized because the oscillations are perpendicular to the direction of energy transfer. So if I imagine unpolarized light, so let's say I had a light bulb. A light bulb or the sunlight gives out unpolarized light. So what does that mean? It means that the oscillations or vibrations are in every plane of oscillation possible that's perpendicular to the direction of energy transfer. So for example, let's say the light was going in this direction. I have particles that vibrate perpendicular to the energy transfer in this plane, or particles that vibrate perpendicular to the direction of energy transfer in this plane. Okay? So what again we're saying is unpolarized light is light that vibrates in all directions, all oscillations, all planes perpendicular to the direction of energy transfer. What we can do is we can polarize this light. So again, if you think about polarized sunglasses, okay, or just the glare, what we do is we basically kind of, you can imagine it like a filter, but it's not a filter, it's called a polarizer. And that polarizer will have basically an orientation. So let's say it's in the vertical orientation. What that means is it's only going to get through parts of the light that are vibrating, oscillating in that same orientation. So only the vertical parts are going to get through. So only the vertical parts of my light are going to get through. So this now is polarized light. So you can see the intensity of light coming through to me if my eyes were here is much less. That's why your sunglasses are good, or just this glare of the water. Because again, instead of having all these orientations, we've only now got that one orientation, so we've reduced the intensity of the light. Another thing we can do is, let's say we don't know if the light is polarized or not. What we can do is we can use a second polarizer. So if I put a second polarizer, again, at the same orientation as that first polarizer, because it's already been vertically polarized and it's still vertically polarized, all of those vertical components can get through and I'm still going to see light. But if I take that second polarizer and I start to rotate it, okay, so we start to rotate it slowly. When we get to that horizontal orientation, so when I eventually get to the horizontal orientation, so I've rotated it, we can see now that it's only going to let through the components of light that are oscillating in the horizontal plane. But again, because we've already polarized it and I only have the vertical plane, and my vertical and my horizontal are completely independent, none of that light is going to be able to get through, so I'll not see anything. Okay? So what we can draw is see how the intensity of light change with the angle of rotation. So again, if we go back when our polarizer, second polarizer, was at the same orientation as the first one. So let's call that 0 degrees. Again, we know that we're going to see the light through the second polarizer because it's going to let through that vertical polarized light. So we're going to see a maximum intensity. Then as we start to rotate that angle, let's say now we get to our 90 degrees again. So we've rotated it by 90 degrees, so it's horizontal. Again, none of those components are going to get through, so we'll see nothing. So at 90 degrees, the intensity is 0. Let's say I rotate it, keep rotating it through. Let's do 108 degrees. Now it's just going to be upside down what it was before, but it's still going to be vertical. So it's still going to let the vertical points through. So what I do now is I can see light. So at 180 degrees, I'm still going to see an intensity of light. Okay, let's rotate it to 270 degrees. 270 degrees, I've gone through again to be horizontal, but now it's going to be in this direction. So again, I'm not going to get any light through because it's already been vertically polarized, so none of that light can get through. So at 270, it's 0. When we get to 360, when we spun it around the whole way back round to where it started with, again, it still ends up in that same vertical plane as the first one. So again, what we're saying now is all of our light can get through because it already has been vertically polarized, and we're going to let the vertical polarizer first. So at 360, we're going to see a maximum. So you can kind of see that we're going to see how the wave changes over time. It goes from maximum to minimum to maximum to minimum to maximum. So when I take my silicon polarizer and I shade it through 360 degrees, you can see the light gets extinguished or gets cancelled twice on the rotation, both at 90 and both at 270 degrees. Okay, so we can use that second polarizer to see if the light is polarized or not. If the light was polarized, again, on rotating it through 360 degrees, the light is going to get extinguished twice. But if the light was never polarized, we're always going to get light through, right? Because if I only have one polarizer, and I have my eye here, what we're saying is, when it's in this orientation, we're only going to let through the vertical components through. But if it was unpolarized light, and now I move it into this orientation, what I'm saying is because it's unpolarized, every possible oscillation, I'm only going to let through the horizontal through. So it's going to let the horizontal through, but I am going to see it. So you can see how we can use our two polarizers to figure out if our light is already polarized or not. And that's a common type of exam question, especially in the multiple choice section. Okay, something else that might come up. It might ask, in one cycle, how will a point on this wave move? Okay, so let's say we're looking at point A. So I want to know later in time, how does point A move? So again, we did our dotted line to show the wave later in time, the energy we moved along. So I can see that point A, this point here, had to move up. So point A is going to move up. Okay, what I know, if it does a full cycle, it's going to move up to its equilibrium, up to its maximum amplitude, back down to its equilibrium, back down to where it started. So in one full period, or one full cycle, T for period, it's going to move up to the equilibrium, to its max amplitude, and down again to that minimum amplitude. Okay, so we can see what it's going to do for one complete oscillation. Let's say we looked at point B. So let's say that's my point B. Point B, we can see later in time, moves down. So what it is going to do is move down to its equilibrium, down to its minimum amplitude, up to its equilibrium, up to its max amplitude. Okay, so again, what we do is we do this little dotted line later in time to see how the particles are going to move slightly later in that time. And again, the key thing is to remember, the particles are oscillating perpendicular to that direction of motion. We're just taking a snapshot over there in time. So maybe they're up here, maybe they're down here, but again, we're taking a snapshot over there in time, and then that's when we take a sketch of that wave.